Start recording. There we go. We are recording. There. So, picking up right where we left off yesterday, I can't change this one to basic derivatives. I can't change this one to a product law until I understand something called the chain rule, which we're not doing till next chapter. So, the only tool in my toolbox right now that would get me the derivative of this thing is the quotient law. So my quotient law says that I can get the derivative of a quotient if the top is differentiable and the bottom is differentiable, and if I know that it's the top. Oh, hang on. Why is this doing this? There we go. It's the top times the derivative of the bottom. Or actually, other way around. Let me start that over. It's the derivative of the bottom times the top. So I'll do just the top. Come on. Times the derivative of the bottom. So d by dx of x squared minus 7x. Right? Low d high minus, or high, I should say, hang on a sec. What am I doing here? That's the other way around. It's right the first time. Sorry. Let me start that over. It's low d high, so the bottom times the derivative of the top minus, I'll put that in a bracket even though I don't really need it, the top times the times the derivative of the bottom.
And remove your hats for O Canada and the treaty acknowledgements.
Okay, let me just pause that while we do O Canada.
We would like to acknowledge with respect the treaty.
There we go. Okay, so that was the numerator. And all over the denominator squared. There we go. The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. All right, I will actually now do the derivative part. So the derivative of 4x is 4, and the derivative of x squared minus 7x is 2x minus 7. As I pointed out in the last example, it doesn't really make much sense to expand the bottom, unless you can see that it would help you somehow, but I don't think that's going to get me anywhere. But I do have to expand the top. So that's going to be 4x squared minus 28x. Sorry, those are x's. Minus 8x squared plus 28x. And that works out fairly nice, because at least the 28x's cancel. And that's going to be my final answer there once I collect those like terms. I'm going to get negative 4x squared over x squared minus 7x all squared. And that's it. That is the derivative. So a typical question might be something like, find the equation of the tangent to this curve when x equals 3, or at the point where x is 3. So basically, I would have to now plug 3 in for the x here, and that would give me the value of the slope. Because this equation is the slope. It's the slope of that line everywhere. So if I want to know the slope when x is 3, I plug in 3. If I want to know the slope when x is 5, I plug in 5. Obviously, the slope of this thing doesn't exist anywhere. Doesn't exist everywhere. Give me an example of a number where the slope here wouldn't exist. How about when x is 0? Because look what happens to the denominator. So that gives me a clue as to what this thing's going to look like. So again, let's do a little bit of review and check my answer at the same time. Oh, I have a question.
So this one, would it be because x squared could be factored?
Yeah, you're right. You could. You have a point. Would I get a slightly simpler looking answer if I factor an x out of the bottom like so? Or hang on. Let me do this pretty like. I'll use a square bracket, and then I'll factor an x out, and then I'll get x minus 7, like that, and then squared. And notice that this really is x, here, let me use my highlighter. This is x squared, right? So technically, this cancels that. Right? You like that? Is that what you were noticing? Yeah, you're right. This is, I suppose, a simpler answer, isn't it? Good point. Okay. Do you get how I went from here to here? Okay. So again, and this is kind of what I was about to talk about anyway, if I was doing my homework and this was the answer I got, I look in the back and that's the answer, do you understand that you do have the same thing they do? You just didn't quite simplify it as much. And if you weren't sure, again, like I look at it and go, I don't know if I made any mistakes, but I look at my answer, I look at the book's answer, and I don't see that they're the same answer. That's where, again, technology can help you out. You can go to your grapher. Okay, which one was this? This was the one, here we go, with 4x right here. So that's this graph here, right? Okay, so that's the graph. Now, what am I expecting for the graph of the derivative? So that's the function. Notice it is discontinuous when x is, what is that? Whoops, I'm moving all over the place here. Hold on. There we go. It's discontinuous when x is, it looks like that's 5, 6, 7, which makes sense, because if you plug in 7, you'll get 0 in the denominator, right? So I don't think the slope will exist at 7. Is there any points where I would cross the x-axis with my derivative? Do you see any points where the tangent would be 0? No, people are shaking their heads no, and that's right, because I don't see any points where I would have a tangent that would touch, a horizontal tangent that would touch this graph. So I'm thinking, okay, all of the slopes as I, can you see my cursor? Yes, you can. All of the slopes as I go this way are all negative, but they're all really small slopes, right? Because they're all very, very, what's the word, not very steep. So I'm expecting everything's negative, but not very far down. And then it gets steeper, but still negative. Then it gets really steep. And then up here, all of these slopes are negative as well. And they're starting off really steep, and then they get less steep. So can you imagine what the slope is going to do? Both of the arms, it's going to have two arms. Why has it got two arms? Because, well, there's a hole here where the derivative won't exist. So there'll be two arms, and they'll both be asymptotes going downward. Can you picture that? Why are they going downward? Because all the slopes here are negative. There isn't a single positive slope on this graph. So let's see if we're right about that. Yep. And then let's see if, okay, that was my answer, right? Let's see if the actual answer and my answer agree with each other. Yep. It's blue, it's purple, it's blue, it's purple. We got it. Okay? So a good question is something like, you saw in the homework back when we first did graphing, questions like, here's the graph of a function, and here's the graph of a bunch of functions, here's the graph of a bunch of derivatives of those functions, and then mix and match and see if you could tell. So if you saw the picture where this is the function, and then you saw this was one of the pictures of the derivative, could you match them up? Right? If I gave you this, and I didn't even tell you what equation it was, could you describe for me the sketch, or make a quick sketch of what the derivative would look like? Okay, that's the idea here. People keep I keep getting messages on EDSB, people saying, how accurate do I have to be when I draw these graphs? Because you had a bunch of homework that said draw a sketch of the derivative. It doesn't have to be accurate. I mean, again, I'm just looking for the basic shape. Okay. And again, I think most of the time when we ask these on tests, we kind of like those matching or multiple choice questions. Right? Okay, so any questions about that one? All right, I think we got a couple more here. Hang on, move over, there we go. Okay, so the D1. Once again, I could try long dividing that, but I can tell right now that would have a remainder, because -1, if I plugged it in here, would not give me a 0. So that does not go into there evenly. So I might as well use my quotient law. And quotient law says that y primed will be So it's going to be the derivative of the, so it'll be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So y primed is, that's going to be 6x cubed plus 6x squared minus, 1 times anything doesn't change it, so I just have to take the opposite of those two terms, all over x plus 1 squared. Okay, so y primed is, looks like I'm going to get 6x cubed minus 2x cubed is 4x cubed, and plus 6x squared minus 1. And boy, that numerator almost looks like a trinomial I could factor, but no, not quite. No, I don't think I can factor anything there. Nope, that's about as simple as I think I can make that one. I don't think there's anything I'm going to do with that one. Okay. And then, okay, once again, quick check on Desmos. So here's the original function. Okay, so what am I expecting for a derivative? Let's see if I can kind of get a picture in my head of what the derivative is about to turn out to be. Well, it looks like there's a 0 right here. So I'm expecting it to cross the x-axis right here, right? Then it looks like there's another 0 here. So it'll cross the x-axis about there. Up to this 0, everything is very sharply negative, right? These are some very, very steep, sorry, very sharply positive. These are some very steep positive slopes. So the slopes are going to be coming down from the positive side very quickly, very steep line. Then it's going to cross the x-axis. It's not going to go down very far because this part isn't very steep. In fact, it looks like it has a slope of about 1, negative 1, I should say. So it might go down about as far as negative 1. Then it's going to cross the x-axis again right here. And then it's going to go up again, not quite as steep going up as this one was, right? So I'm expecting something kind of like a parabola, but not symmetrical, because one side's steeper than the other. And it does cross the x-axis twice, and between the two crossings, it goes down to, I'm going to say, around -1 or so. Any questions? Anybody not seeing how I'm seeing that? Question? Okay, remember what the derivative is. The derivative is the slope of the line, right? So what's the slope of the line? Can you see my cursor? What's the slope of the line right there? 0. What's the slope of the line right here? 0. So the graph, just a sec, the graph of the slope has to cross 0 here and here. Or when x is this high, so right there, and when x is this far over, which is right there. Okay, so let's see. So let's see if we're right about that. There we go. And then a very steep line over here. And let's see if my answer agrees with that. Because oh, wait a minute. Is this mine? Yeah, this was my answer, right? Yeah, 4x cubed. Okay, let's see. Do we agree? Yep. Black, purple, black, purple. So there we go. I don't really care about this left line. It was this part that I was kind of concerned about, and that's the part I got. Okay. All right. Next. One more. All right, what am I going to do with this mess? Well, I'm going to change this to x to the 1/2 all over x cubed minus 6x. And then I'm going to find my derivative. And again, that's going to be low d high. And of course, the derivative of x to the 1/2 is 1/2 x to the negative 1/2 minus high d low all over denominator squared. Okay, what can I do with this mess? Well, I think what I will do is I think I will switch to radicals and then play with the radicals. So radicals and reciprocals. I'm going to get rid of the fractional exponents and the negative exponent. So this is going to be 1/2 times x to the negative 1/2. That's like saying 1 over 2 root x. So everybody get what I did? I combined this guy and this guy to make that guy. So far, so good? Okay. And then the other side, I'm just going to change that to root x times 3x squared minus 6 all over x cubed minus 6x squared. Okay, what am I going to do with that? Well, I'm kind of looking at this like this thing here. I'm just going to maybe 1 times anything. I can think of this as having a denominator of 1, right? So I'm going to say that that's x cubed minus 6x all over 2 root x minus, here, how about root x times 3x squared minus 6 all over 1 all over x cubed minus 6x squared. And then I'm going to combine these two things into one common denominator. So I'm going to multiply by 2 root x, which is going to make this radical here kind of go away. So I think I might get some like terms I can collect here. So this is going to be x cubed minus 6x, and then I have 2 times root x, which is 2x times 3x squared minus 6, all over 2 root x. And instead of dividing by this thing, why don't I change that to times by its reciprocal? And then, I'm kind of out of room here. Let's collect like terms. I'm going to have an x cubed minus 6x cubed is negative 5x cubed. I'm going to have minus 6x plus 12x, so that'll be plus 6x, all over 2 root x times x cubed minus 6x squared. And that's about as much as I think I'm going to simplify that. I'm thinking, well, I could try to factor an x out of the top, but it wouldn't I guess I could. I could factor an x out of the top and cancel it out of an x from the bottom, but it wouldn't make it that much simpler. I guess I could. This is kind of what we did on that one 2 examples ago, right? Oh, wait. There. Put a square, oops, put a squared there. And okay, so if I factored an x out of the bottom here, then I factored, that'd be 2 times x times root x, and this would be, let's see, if I factored an x out of that, then this is an x squared minus 6. Does everybody get that there has to be another x here, because the x I factored out of there is really an x squared? There. Can you tell that those two things are the same answer? And once again, if I'm not sure, what do? Use the technology to help me. And if anybody does have a graphing calculator, those of you who are going on to AB calculus, they will make you use the graphing calculator, because all of their tests, you know, you're not allowed to use the technology you can like communicate with. Question? Are you wondering where I got this extra x from? Oh, right, you're right. Thank you. I lost my squared. Good eye. Anyway, the point I was making is if you do want to try graphing these with a graphing calculator, it's a little more complicated than graphing on Desmos or on GeoGebra or on Wolfram Alpha or whatever online technology you're using. But it's doable. The hardest part of graphing with a graphing calculator is figuring out the window so you can see your graph, because you have to basically enter that. People who have played with graphing calculators are shaking their heads. Yes, you graph something and your screen shows you nothing, because now you have to figure out, okay, at what scale can I see this graph? And you have to really figure that out. Whereas on an online grapher, it's really just a matter of saying, oh, I just want to just make the screen bigger, make the screen smaller, just drag your fingers over it, and it's super easy. On the graphing calculator, you have to actually enter numbers to look at the scale. So anyway, the thing we just graphed was this thing. My answer, okay, again, what does that look like? This is getting hard to do in my head. But certainly it has a 0 here, right? The tangent here is 0. So I'm going to cross the x-axis right there. And then it's going to be very steep as a slope. In fact, it's going to be basically a positive line going up that way. And then it's going to be a negative line going down that way. Then what's the derivative of this thing? Well, again, all of these are negative, so that arm's going to go down that way. And then it's going to flatten out because that almost has a slope of 0. So that's what I'm expecting. And yep, that's what I got. Right? And then this is my answer. Please be the same graph. Yay, it's the same graph. I was for a second not sure if I did that right, because I don't have an answer to give you this. Okay, so any questions? All right. I'll stop my video now, and I'll pick some questions. I haven't updated the blog for today yet. I'll pick some questions from the Quotient Law assignment for you to do.